Okay, good morning and welcome to lecture number 29. In the last lecture, we looked at Prim's algorithm. We saw the correctness, and we were looking at implementing, in particular, the step 2, which is part of a loop, basically to extract minimum weight edge, which is outgoing from the partial tree that Prim's algorithm has built so far. Okay, so yeah, so we saw, I just stated without much proof that the naive implementation, so implementation using adjacency matrix, will require order of n time per iteration, so it will be order of n square. Okay, so we'll use what are known as heaps. So using heaps, we can improve this to order of m log n. Okay, so this is kind of improvement. I'm assuming. Okay, so this is, yeah. So this improvement is significant when number of edges m is smaller than n square. Okay, or say smaller than n square by log n. Okay. Further, we'll also see further improvements where using Fibonacci heaps or Fibonacci heaps, which is a different implementation of heap with certain certain modifications, particularly the way how we merge two heaps and so on. This can be improved to order of m plus n log n. Okay. So towards the end of the lecture, we were introducing heaps. So I'll just go over the introduction of heaps and see the basic algorithms for heaps. So a heap is a data structure. So various operations that are allowed or can be performed on heaps and their complexity. And then towards the end of today's lecture, we'll see how we can use heaps to implement the step 2 of Prim's algorithm. Okay. So using what are known as priority queues, which can be implemented using heaps. Okay. Just abstractly, heap is an array object which is viewed as a complete binary tree. It's essentially to store values. Okay. We'll imagine that each node of the tree is an element of the array. Okay. So usually we keep two attributes for the array length, that is length of the array, and heap size. So heap size is number of elements in the heap. So what we want is heap size is at most the array length. In most of our cases, we'll assume that heap size is equal to array length, but there could be subroutine calls where heap size is significantly smaller than the array length. Array is bigger. Okay. So the way we implement this, so heap is basically a binary tree. Okay, we can call it as almost complete binary tree or almost full binary tree. We'll always assume that the root node is the first element in the array. Okay, so the array A1 is a root node. So here root node is has value 16, and then for a given node, its left child in the tree is A2i. So assuming that it is within the array limits. If it is beyond the array limit, then I is a leaf node. Okay, that is if 2i is more than array length, then we know that I is, or A of I is a leaf node. Okay. Left child is element of index 2i, and right child is element of index 2i plus 1. Okay. So using this, you can see that for a node, parent of I is I by 2. You take floor. If it is an odd number, I is an odd number. Okay. So for 1, there is no parent. Okay, because I by 2 floor is 0. Okay, so A0 is non-existent for us. Okay, we assume arrays are indexed to 1 to n. Okay. So in summary, all we need to know is these as functions. So parent, left and right. So for a given index I, so parent of I is at index I by 2. You take the floor. And the left child is index 2i, right child is index 2i plus 1. Okay. So heaps become interesting when we introduce order into the values stored in the heaps. Okay. So there are two variants based on the ordering. One is max heap and one is min heap. Okay. So for max heap, the condition is the key or the value of parent should be more than, that is, array at the parent, array value corresponding to the parent of a node should be greater than or equal to the value at the node. That is, a of parent of I is at least a of I. For min heap, it is the other way around. That is, a of parent of I is less than or equal to a of I. Okay, that is, parent will have smallest value among the children and parent. Okay, so for example, so this example, this is a max heap. So you can just verify. So look at node 1. So value of node 1 is more than both of its children. Value of node 2 is more than both of its children, which are 4 and 5. Okay. So value of node 3 is more than both of its children. So this will be strictly more if the values are distinct. If the values are repeating, it could be greater or equal to. Okay. So you can see that this is a max heap. It satisfies max heap. So similarly, you can imagine min heap. The relations are flipped. That is, the parent should be minimum among the children. Okay. So all right. So one thing is, if you consider a binary heap with n elements. So when I say n elements, not just n leaves, so including the internal nodes. So each is considered as an element. Okay. The height of a heap is theta log n, the way it is defined. Okay, it's almost complete binary tree. So what do I mean by that? So the leaves, right? So the difference, level difference. So let's say this is level 0, level 1, or level 1, level 2, etc., etc. So the level difference between two leaves should be at most 1. Okay. So if I take this leaf and this leaf, so this is, so let's imagine this is level 1, 2, etc. Okay, 1, 2, 3, 4. So this leaf with value 1, that is array element index location 10, and leaf with value 9, array index location 9, they are at a height difference of 1 or level difference of 1. Okay, so height is the dual of level. So the height is, let's say, 1, or possibly I think some people also refer to it as 0, 2, 3, 4. This is height. This is level. Okay. So this property is required in the sense that the height difference between two leaves or level difference between two leaves should be at most 1. Okay. So that means I cannot have a leaf at this level. Okay. I cannot have a leaf at this level, or I cannot have a leaf at this level. This is forbidden. Okay. So this is not allowed. So using that fact, we can easily argue that height of any binary heap with an elements is upper and lower bounded by log n. Okay, it will be lower bounded by log n because any binary tree can have a binary tree with of height, say h. It can have at most 2 to the h plus 1 nodes, right? Into 2 to the h plus 1 minus 1. Okay, so that way it is lower bounded by log n. So you can also see that it's upper bounded by log n because of this. So the height or level difference between any two leaves is at most 1. Okay, because of that condition. I'll leave this part as an exercise. We'll not spend time on it. So like I said, there are two kinds of heaps, min heaps and max heaps. One observation is for a min heap, if you look at the root element, the value is minimum, okay, among all values in the heap. Similarly, for a max heap, you can argue that the root element stores the maximum value. Okay, so you can just check here. So here the maximum value in the array is 16, and by the heap property, right? So if you compare any two, the value at their parent should be larger. Now again, if you compare any two, their parent should be larger. Similarly, if you compare any two, their parent should be larger, and so on. So that way you can argue that the value at the root is maximum. I'll just leave it to you to write down an simple inductive proof based on the structure of this tree here. Okay. So what I mean is, inductively you assume that for whole of this portion, the max is root here, the max is root here. Then you know that this value is greater than these two max. So hence this is the max. Okay. Yeah. So I'll skip that part, but this is an important information for us. Okay. Okay, so now we look at operations that are useful for us. Okay, so there are like one important part is to ensure that your heap has heap property. So we call that corresponding procedure as max heapify. So for min heaps, it will be min heapify. Okay, so you are given an array A, okay, and an index I. Okay, so we'll assume that the left child and the right child, they are as subtrees, they are max heaps. They represent max heaps. Now what we are required to do is, at the ith node, we ensure that the heap property is satisfied. So what we have is, potentially at the ith node, the heap property is violated. So we need to modify the heap so that starting from AI, so you take AI as the root, the corresponding subtree should have heap property. Okay. The second procedure is to build heap. So given an array of n elements, you build a heap structure on it. So you are allowed to move values around so that you get a heap structure. Okay. And yeah, this is for inserting an element into a max heap so that the heap property is not violated, and removing an element. Potentially you need to increase or decrease the value of a node. Okay, so in the case of max heap, it's increase. In the case of min heap, it is decrease. Okay, yeah, so there are corresponding dual versions for min heap. So what I'll do is, following CLRS, I'll just discuss max heap now. Yeah, CLRS discusses max heap because they're also interested in sorting using heaps, so for which people use max heap. Okay, though you can also sort using min heaps, no big issue. Okay, yeah. Any questions so far?
Hello? Hello? Yes, sir?
Yes, I can hear you.
Am I
Yeah,
audible?
please. Yes, you
So,
are.
okay.
Am I audible?
Uh,
Yeah.
yes. So, you are saying that we have max, like heap increase key here. You are also
Yes.
saying that we also have a function heap decrease key for max heap also.
No, for min heap. I mean, see, usually the functionality, right? I mean, it is called increase key. Usually, it is basically updating the value. Okay, but traditionally, it has been, so for max heaps, it's called increase key, and min heaps, it is called decrease key. Okay. So
But
I
I
mean,
am
the
thinking that whenever
nomenclature
we use,
is that it's, yeah. So it's essentially, it's not increase. So you can just call it as change the value or update the value. Okay.
okay, sir.
It's just a nomenclature. Yeah. Yeah, so in the next 30 minutes or so, I'm going to discuss these procedures in a bit more detail, max heapify and possibly build max heap. Okay, and these operations I'll just leave to you to see that this can be implemented fairly efficiently. Yeah, and after that we are going to look at a structure which helps us in implementation of Prim's algorithm. Okay. Okay, so this is a procedure written as it is from copied as it is from CLRS. Okay, so max heapify is a procedure which has an array and an index. Okay, so like I said here, so you're given an array and index. What you can assume is, if you take left of I and right of I, look at the corresponding trees, they satisfy max heap property. Now what you want to, so but there could be a violation at the top, that is AI and A left I, A right I may not satisfy the max heap property. We need to do necessary modifications to the heap so that AI is also a heap. Okay, so you can imagine this. So here A is this array, so the example that I had given, and I is 2. Okay, so here if you look at the subtrees, the left of it, so it satisfies heap property 2, 4, 2, 8, 14, and similarly the right satisfies heap property. But however, there is a violation here. Okay, so now how do we modify so that we can ensure the heap property? So the procedure is not at all non-trivial. What you do is you look at the children, look at the maximum of the values. Okay, if the maximum of the values is smaller than the key value at I, you don't do anything. It satisfies the heap property. If it violates, the maximum of the values will be larger. Okay, so what you do is you push that value upper. So in the next iteration, what you do is you push this upper. Okay, now what is the effect of it? Now these three nodes locally satisfy the heap property, but since I have pushed a value down which is potentially smaller than the original value it was, so here there could be a violation, right? Can there be a violation here? You didn't change anything, right? We didn't change anything here, so there may not be a violation here. So wherever you are pushing this value down, basically swapping these values, so there could be a further violation. So you will have to call this procedure recursively further. Okay, so there is a recursiveness involved here. I mean, there is a chain reaction that is happening, but the chain reaction is kind of controlled. We'll see that it really does not harm much. It can go as far as the height of the heap is. Okay, so this is essentially the procedure. All you do is you locally compare the node I with its children, take the maximum and push the maximum to position I, and the value of I is pushed to that position with which held the maximum already, and you repeatedly apply the procedure. So recursively apply the procedure on this subtree. Okay, so that's exactly what is described here. So what you do is you look at the indices of left and right. Okay, now you just see if these are within the array bounds or not. Okay, so if one of them is not, so this index large is set accordingly. Okay, now so what you do is you just pick the index such that the value is largest among these three values. So these are the three values you are interested in. Okay, so let me mark it with dark. So largest at the end of these three steps should be holding the index such that among three it is a maximum value. So the largest here will be 4. Okay, so let's look at it. Yeah, so let's say ignore this corner cases for now. Okay, so what we have is, sorry, and this is a fairly optimized procedure. Okay, so so let's ignore this portion, this boundary size thing. Okay, so if array of L is greater than array of I, then you take largest as I, okay, and sorry, largest as L, sorry, else you keep largest as I, okay. So among the left child and the node I, this after this step 5, largest holds which value is largest. It's like computing maximum, it's the same thing, okay. Now again, so this is a condition, it says that okay, R and L are within the heap size. Now if AR is greater than A largest, you change largest to R, else you keep largest as it is. Now if largest happens to be I, then there is no violation of heap property here, so nothing to do, okay. If largest is not equal to I, so then what you do is you exchange AI with the largest value. So in this example, so you exchange A of I, which was 4, with the A of largest, so largest is 4 here, okay. So you swap these values. Then what you do is you recursively call max Heapify on the largest. So you call max Heapify on this, okay. So yeah, that is a procedure. So now these conditions are to ensure that L and R are valid. See, in case when I is a leaf, right? Then or yeah, so in case when L is more than the heap size, that means I is a leaf, right? If L is more than the heap size, then R is also going to be more than the heap size, okay. So that means I is a leaf, or it could be that I has only left child, it does not have right child. In that case, it could be that R is more than the heap size, okay. Yeah, so these are basically conditions to ensure that you are not going beyond the array boundary, okay. Otherwise what you are doing is you are looking at these 3 values, computing the index which holds a maximum value. So in this case it happens to be index 4, the maximum value being 14. You just swap these 2 values and recursively take this index as I and compute run the algorithm recursively, okay. So this is how it looks like. So the next call, now you have these 3. So now a swap happens here, okay. Now when you make a recursive call here, now L and R both are out of bounds for the heap, okay. So they are out of bounds for the heap. So 2i is and 2i plus 1 are greater than the array length, or even in fact heap size. So the procedure will return. So the procedure will not do anything here, okay. So yeah, so the largest will be equal to I and the procedure will halt, okay. Is the procedure clear to everyone, particularly those who are seeing it for the first time? So only thing here is there is a chain reaction, okay. So but the chain reaction happens only one side, right? Because you are swapping the value at only one, so the chain reaction happens only at one side. Yeah. So if you look at this, this now satisfies the heap property. Yeah, sorry. Okay, if there is no question, we'll go ahead. Okay, so let's just do complexity analysis. Yeah, can somebody tell me what is the complexity of this procedure?
Login.
Sir,
Log
you're
n, okay.
going at only one side of the
Yes.
hello.
Yeah.
So
Go
you're
ahead.
going only at one side of the tree, like either left or right at any one point of time. So it will be the height you're traversing.
Yeah, it's basically
So
height. Hence, so using this exercise, we know that the height is theta log n, right? it's going to be theta log n.
Yes, sir.
In fact, order log n. Yeah. So yeah, so the complexity is going to be order of log n. In fact, we can say theta log n because the height is being theta log n. Okay. Height is also lower bounded by log n. So in for certain, it depends on the index I, of course. Okay. So the reasoning is, so I'm not going to prove this rigorously. You can write a recurrence and prove this. Okay. Okay. So yeah, you can write it as, so T of h is less than or equal to, so T of h minus 1 plus order 1. Okay. Where h is the height of the tree rooted at ai. So we know that maximum value for h is log n. So T of log n. So if you solve this recurrence, this will be bounded by order of log n. Okay. Or in fact, if you substitute n for this, so T of n is going to be order of n. Okay. So this is one way of doing it. I mean, you can just write down the recurrence. Okay. So you're making only one call. So hence it is T of h. So now the height certainly decreases, right? If you go one level down, the height is going to decrease. So height is, yeah, I don't know what is an tradition here, but I call this as height 1, height 2, height 3, height 4. Okay. I think some textbooks say this as height 0, height 1. Leaf node is treated as height 0, I think. Okay. Nevertheless, it does not really matter. So yeah, so the complexity of this procedure is order log n. Okay. So right now there is no, I mean, you can ask me what is application of it, particularly those who are seeing Heap for the first time. So it is a crucial procedure. It can be used, for example, to build Heap, it can be used, or when you remove an element or you add an element, this can be used. Okay. So yeah, so the next procedure that we are going to see is build max heap. So remember that the input here is, so input array A of n elements, output modified array A, so that it is a heap. When you are given an array, there is no guarantee that it is a heap. Okay. So what you want to ensure is the array at the end of the procedure should be a heap. Okay. So yeah, so this is a procedure. So before reading this procedure, so let's just describe what it is doing. Okay, so then we'll come back to the procedure. So first thing is, when you have heap structure for an array, okay, so binary tree structure for an array. So let's just stare at the array. Okay, so let's that should be a blank space. Yeah. Okay, so let's just look at this array. Index 1, index 2, etc. up to index n. Okay. Let's say this is n by 2, say floor. Let's take this as n by 2 plus 1 and so on. Okay. So suppose we have imposed a tree structure on this the way we have mentioned, that is right child of node I is 2i, left child, right child is 2i plus 1. That is parent of node I is n I by 2 taking floor. Now what can you say about this? What can you say about these values? What are they as tree with respect to the tree? So take n by 2 plus 1.
Leaves.
They have to be leaves, right? Because if you want to see right child of this, so that a left child of this, let's say, so 2 into n by 2 plus 1. That is more than n, right? I mean floor of n by 2 plus 1. there's a floor here. I didn't write it so that it looks neat. Okay. So floor of n by 2 plus 1, right? That can exceed n. So these, the only way for these are leaves. So these are leaves. Okay. Now what are their parents? The parents are here. Their parents are here. Okay. So for any leaf, if you see it as a heap with a single node of height 1, it is a heap, right? No matter what the value there is. So say this is value 10, this is 5, 15, and so on. So what we are going to do is at this leaves, so we are looking at these leaves, so n by 2 plus 1, etc., n. So we'll see this as leaves. Okay. So now we know their parents. Okay, we can compute their indices. So what we are going to do is we are starting from index n by 2 upwards. Okay. So we are going to apply the Heapify procedure. So you'll just look at this. Now apply the Heapify procedure. Okay. So for this, say this is what will be the parent. Okay. So n by 2 plus n by 2 will be the parent of this, right? So you first look at this and apply the Heapify procedure. This will be n minus 1. Okay. So apply the Heapify procedure. What happens? Locally, this becomes heap. So this becomes green. Similarly, when you do one pass, whole of this would become green. And then you go one level up. So these were all green. Now apply the Heapify procedure again. These will become green and so on. So at the end of the procedure, the root will become green. So we'll have root with its children being green. Now we run the procedure on the root, which is element 1 in the array. Okay. So that's exactly what we are going to do. So at the leaf level, we know that, see, Heapify procedure, what does it require? So you give it an index I. It should be that the left and right, that is indices 2i and 2i plus 1, represent heaps which have max heap property. Okay. But what is the smallest thing, smallest heap that satisfies? Because see, array is given to us. We have no information on the array. It can be anything, right? But if you consider leaf nodes in the tree imposed on this array, they are by default heaps, max or min, it does not matter. Okay, so we are only demonstrating for max heap. So max heaps. Okay, so then we can build upwards. That's exactly what the procedure is going to do. Okay, so yeah, this is the English description of whatever I've said. So the array indices n by 2 plus 1 onward until an are leaves of the heap being built. Okay. So now the algorithm assumes that leaves are valid, max heaps, and applies max heapify in a bottom-up fashion to the trees above the leaves. Okay. So the invariant is for iteration when we consider index I, the children of AI, that is a2i and a2i plus 1, as roots of valid max heaps. Okay. And then max heapify ensures that the tree rooted at AI is also max heap. So you have a larger heap. At the end, the index is going to be 1. When you call max heapify a1, that's going to convert the whole tree into, or array into a heap structure. Okay, so that's exactly what is being done in this procedure. So you're given an array A. Okay, so you set the heap size as array length. So you're assuming that the whole array is to be heapified. Okay, so what you do is you start from n by 2. You take floor. Okay, to 1. So I goes down from n by 2 to 1. Okay, so you call this procedure max heapify AI. Okay, so what is the invariant? So I had written an invariant, right? So invariant is for iteration I, we have the children of AI, that is a2i and a2i plus 1, as roots of valid max heaps. Okay. So let's see if it satisfies. So let's say length is n. So what is the first iteration? So I is, sorry.
Sir, sir, is it
Yes.
audible? Sir,
Yes,
like
yes, please go
one
ahead. Yeah.
doubt. So if you consider that invariant part, right? I just have a doubt. Is invariant is equivalent to the
Yeah.
inductive hypothesis? Induction hypothesis?
Yeah, so I mean, you're right, you're right. So see, usually, I mean, any inductive proof of correctness of an algorithm, you maintain an invariant and inductively prove that that invariant is maintained. That's all. Yeah, you're right.
Okay, sir. Thank you.
So invariant is a predicate or a property which should hold at every iteration. Okay. Now, so what you say is like, okay, from I to I plus 1, in this case, I to I minus 1, the invariant is maintained. So hence, overall, we have the invariant. And at the end of the procedure, that invariant should imply the correctness. That is, your structure, in this case, structure, should satisfy the required property. Okay. Yeah. Yeah. So did I answer your question?
Yes, sir. Yes.
Yeah. Okay. Okay.
So it just proves the induction
Yeah. So let's
hypothesis
look
at
at.
every step.
Yeah, that's true. That's it. That's it. See, what we have to do is, so for if you prove this invariant by induction, that's it. That gives. So this I mean this is a statement saying that okay, this algorithm maintains this invariant. We are yet to prove this by induction. I mean, I'm not going to prove it by induction, but it's a simple argument based on the correctness of max Heapify procedure. Okay. Yeah. So okay, so just to demonstrate, so what is the first value of I for iteration 1? What is the value of I? It is, so let's say array length is n, so n by 2 floor. Okay. So next iteration 2, I is n by 2 floor minus 1 and so on. Okay. So iteration j is I is n by 2 minus j minus 1 or plus 1. Okay. That is it. Okay. So I'll demonstrate this procedure with an example. If you have any question on the procedure, please let me know. So all we are going to do is we are going to start from this index to apply max Heapify on each of these. Okay. So what happens is it's basically happening this way. Okay. So this is a starting point. So the children are valid heaps. So this portion is Heapify right now. So when I move one index further, basically moving like this. So the children will be n minus 2 and n minus 3. They will be Heapified and so on. So you're basically scanning this tree this way and doing heapification. You go back, scan this way, go back, scan this way, go back, scan this way. This is exactly how the procedure works. Okay. So yeah, if there is a question, I'll wait for a minute and then I'll give a demonstration, give an example. Correctness is fairly straightforward. Okay, so basically this induction applied on this iteration, I mean this invariant. So you prove that this invariant is satisfied, which is at once followed by the correctness of max Heapify. Yeah. Okay.
Hello, sir.
Okay. So yeah.
For I running, like
Which slide?
whenever your children are leaf nodes, the invariant
Huh.
is true. But how do we say that for every I it is true? Like it is, like we can see that it is true, but how do we prove it?
No, that is by how the loop works, right? So if I is true, or say for up to I it is true. See, to begin with, I equal to n by 2 plus 1 to n, it is true, right? Okay. So now what you do is, for if all we need to argue is if up to I it is true, I minus 1 also it is true. That is ensured by this max Heapify procedure. Okay, so that is for indices up to I. If this is true, okay, then for index I minus 1, this is also true. That is immediately ensured by the Heapify procedure, because for I minus 1, what are the children? 2 into I minus 1, 2I minus 2, and 2I minus 1. So these satisfy, right? Now Heapify procedure ensures that these three also satisfy. So that means we also have the statement for I minus 1. That is all. Only thing is the induction is going from I to I minus 1. Okay, that's the only problem here, nothing else. The induction is not I to I plus 1.
Sir, okay, just like not understanding this part. How
Yeah.
is max Heapify ensuring I minus one's like heap property when we are only passing I?
No. Okay. We are assuming up to I it is true. Okay, or maybe I'll change the statement. We are assuming that up to I plus 1 it is true. Okay, n to I plus 1, the statement is true.
Okay.
When you run I, okay, when you run the procedure for I, so potentially at AI the condition is violated. Okay, when you run this procedure I, so max Heapify procedure, it ensures that for AI also it's true. That is all. So that means, but it does not violate anything else, right? The max Heapify procedure does not violate anything else. So it is it. So what I was trying to do is induction from I to I minus 1, but you can also take it as like I plus 1 to I, because we are talking about iteration I. Well, this is I think there is a problem here. So for iteration I, this is not A of I. Okay, this is not A of I. So for iteration I, what is the value? A of n by 2 minus I plus 1, right? Yeah, so that is what. This is not AI. N by 2 minus I plus 1. So whatever, 2 of that value. Probably that was the confusion for you.
Yes, sir.
Yeah, so this was not precise indexing. Index should be A of n by 2 minus I plus 1, 2 into that. 2 into n by 2 minus I plus 1, 2 into n by 2 minus I plus 1 plus 1. Okay. Yeah, sorry. So AI, I mean, it will feel like, okay, iteration 1 is A1. No, that is not correct. Yeah, this is.
Sir, okay, even if we are running backwards, hello? My question is still is like for the leaf nodes, we know that they are the roots of valid max heaps. You are saying by induction, the next step, like if from I to I minus 1, no, I should not call it like that. So
Yes.
since we are running backwards,
No, now you can have iteration I to I plus 1. With this notation, you can have iteration I to I plus 1.
okay, so how are we saying that
Yeah.
from I we are saying that I plus 1 is valid?
No, not from I. So what we need is up to. So, okay, so what probably I understand your confusion. So there's a lack of preciseness in this statement. What I have to say is for iteration I, so for all j, okay, so for all j greater than or equal to this number, so children of, okay, so the precise statement I can just make it very precise. Okay, so the statement is for iteration I or before iteration I, for all j greater than or equal to or greater than n by 2 minus I plus 1, aj is a root of a valid heap. Okay, that is all. This is the correct invariant. I mean, very precise invariant. Okay, so for every index above it, it should be a root of a valid max heap. Okay, so that means if I consider a2j and a2j plus 1, okay, I'm just considering this as j, let's say this is j, just to simplify. Okay, it is going to be root of valid heap. Now you apply max heap procedure, so what you have is aj is also a root of valid max heap.
This is because of the max.
So that is the induction. Yeah, it's because of the max heap effect, that's all.
Okay, are we going to prove this invariant?
Yeah. I'm not going to prove. I just stated it, that's it. I'm skipping it.
Okay.
I'll just demonstrate the algorithm with an example and that's it. No, since you wanted preciseness, I'll just put it as precise. It's always, sometimes it's easier, write it at the cost of preciseness, write it easily readable. Okay, so yeah.
Okay, sir.
Yeah. Okay. I'll just demonstrate the procedure here in this using this same array that we had before. Okay, with slight ordering change. Okay, in the end, it should be the heap that we have built. Okay, so suppose this is an array of 10 elements. Okay, so indices are 1 2 up to 10. Okay, so up to index 10 9 8 7 6. Okay, so this we can assume as heaps. So these are valid heaps. Okay, we are only looking at index 5. Okay, so that is going to be first one. So if you look at this procedure, so I is n by 2 floor, which is 5. Okay, so first iteration is going to be 5 here. I is going to be 5. Okay, now you run the Heapify procedure, so there is no change. Okay, so this is also a valid heap. It stays as it is. Index goes down one further. Okay, that is index position 4. So the next value of I will be 4. Okay, when you apply Heapify procedure, what happens? So 14 will come upwards. Okay, 8 will stay as it is, so it will get swapped with 2. Okay, so 14 becomes 2 and 2 becomes 14. Okay, so that is it. So at the end of iterations with indices 5 and 4, so we have these trees as valid trees. So all of these are valid heaps. This is valid heap, this is valid heap, this is valid heap, this is valid heap. Now I becomes 3. Okay, so that is index position 3. The value here is 3. Okay, so now you run Heapify on 3. So what will happen? So 10 will come above, right? That's exactly what has happened. So 10 came above. So now what is the invariant that we have? All these trees are valid heaps. Next iteration is I is 2. Okay, the value at position 2 is 1. If you look at this array, sorry, value at position 2 is 1. Now you run Heapify again on 1. Okay, so now what will happen? So the maximum of the values will come up, which is 16. So 16 goes up. It is swapped with 1. Then again the Heapify will run further on this. So 1 will come here and 7 will be here and 16 will be here. That is how it will look like. So at the end of this iteration where the value of I is 2, so what we have is this subtree as well as this subtree is heap. That means whole of these subtrees are heaps. Okay, so now we run the procedure Heapify with I equal to 1. Okay, so then it does a local comparison, replaces 4 with 16. Okay, it will push the value, but where will it push? Here. Okay, it will again compare. It will push 4 and swap it with 14 down, and then again it will push. So 4 will come here. Okay, so this is the final heap. So if you look at this, this is the final heap. Okay, so this is how the procedure runs. So when I run I, so all indices which are like higher than I, the corresponding binary trees. So each will have a rooted binary tree, right? Each node will represent a rooted binary subtree. Okay, so they will all satisfy the heap property. So that is being ensured. Okay, so that is ensured using this invariant here. And like I said, the more precise way is like you should have a quantification for every index. Okay. So each. Okay, sorry. Yeah. Any questions on this? So I'll skip the formal argument of correctness. I'll not go over it, but I'll just request all of you to write down the formal statement, the statement what I have written here, and prove it by induction. Okay. Only thing is the iteration value I goes from I to I minus 1. That is something you have to keep in mind. That's all. Okay. It's not I to I plus 1. But if you state in terms of iteration, right? Iteration I, that iteration I to I mean, so the iteration count goes from whatever j to j plus 1, but the index goes down. Okay, so that is something that you have to keep down. So I basically goes down, but if I take iteration count, right? So iteration 1, iteration 2, that way it increases. So that is, you can, yeah, you can think about how to write down the induction hypothesis and so on. Okay. Okay, if there is no question, just to summarize, so each max heapify call takes order log n time. So the complexity of the algorithm, since we are making n by 2 iterations there, so overall time will be order of n log n. Okay, so the time complexity of building the heap, given an array of n elements, building the heap can potentially take n log n time. But however, there is one catch: this analysis is not completely tight, because this max heapify, right, when you're calling arrays of height potentially smaller. Okay, so the first n by 4 calls here, first n by 4 calls will be to an array, a heap of height 1, right? And the next n by 8 calls will be to height 2, and so on, right? Or height 3. So if you say this is height 1, then that will be height 3, and so on, right? So potentially it is, so log n is an overkill. The worst case height is log n, yes, agreed. But not every heap that you are going to call heapify on is of height log n, right? So that way this is kind of overkill. This is asymptotically not tight. So we can actually improvise the analysis. I just write down the analysis. So in fact, the tighter analysis gives order of n time. The idea is fairly simple. Okay, so what you do is, so this I'll leave as an exercise. I will not prove it. It's fairly simple proof. At height of h, a heap can have at most n by 2 to the h plus 1 nodes. Okay, so yeah, so this assumes that the starting height is 0. Okay, so then this seems to be fine. Yeah, so you can have at most 2 to the h plus 1. Otherwise, I will have to have it as 2 to the h. Okay, so for each of this node, the cost of max heapify will be going to be order of h. Okay, so we can take this into account and do the counting. Okay, so now how many nodes correspond to heaps of height h, roughly n by 2 power h. Okay, or I mean I have taken h equal to 0, so this will not be 2 power h plus 1, this will be 2 power h. Okay, sorry, just erase this. This completely depends on the nomenclature. Okay, h or h plus 1. So you will incur a cost of, let's say, some constant times h for how many nodes? N by 2 power h nodes. Okay, so the overall, I mean, if you take this summation, this becomes n into summation h by 2h, h going from 0 to log n. Okay, I'll just leave it to you. You can either prove it by induction or do an integration. You can just approximate by integration. So this summation comes down to 2. Okay, so this is bounded by, maybe I have written it here. Yeah, so this is bounded by at most 2. Okay, so therefore this summation is order of n. So all you are doing is a more careful count. So if you look at this tree, let's go back here. Okay, so what you do is, see, all these nodes will incur a cost of 2 or a constant multiple of 2 for the Heapify procedure. All these nodes will incur a cost of 3 into some constant. All nodes at this level will incur a cost of 4. Okay, so that is the count that we are doing. Okay, so how many are incurring a cost of, let's say, cost of 2? That's exactly how many nodes are here. Okay, so we are also, so one thing is in this summation, we are also assuming that we are also processing the leaves, the summation.
Sir, the second last
I can
level.
go as well as.
Hello.
Yeah. Sorry. Yeah.
Yes,
Yeah.
sir. The second last level will incur a cost of 1, na?
Which one? This one. This one, right?
Yes, sir.
Yeah, I have taken it as 2. I mean, it's just a constant multiple. Like I said, right? So I have this habit of taking height as 1 here, but I think many textbooks take it as height as 0. Okay, so yeah, that's why I said this is height of 2, so it's a constant multiple of 2. That's what I said. Okay, which is 0.52 is also fine, right? So that's yeah, we'll just put everything under this constant multiple there. Okay, yeah. So that is why, I mean, since because of the notation that I follow, this is not exactly h plus 1. This is just h. Okay. So yeah. No. Okay, that's fine. Leave it. So this summation, I won't tell you exactly how do you get it. So there are multiple ways. You can just prove this by induction on h, or you can also prove it by integration. So you just approximate this by integration, h by 2 or x by 2 power x dx 0 to infinity. That will give the bound. Okay, so yeah, this is bounded by a constant. So overall complexity is going to be order n. Okay, but nevertheless, we are not really going to be relying. It is fine for our applications even if the complexity is n log n, because there are other dominating time bounds which will require order of n log n time. So that way it is not really crucial for us. But nevertheless, I request all of you to refer to CLRS for details of this. This is chapter number 6. Okay. Okay. Oh, it's already 9. Okay. So yeah, we'll stop for now. So in the next lecture, we are going to see how we are using this for prims. So I request all of you to go over the heap sort section in CLRS. Most of the things are in full detail over there. Okay, so most of these are proven. I think the Heapify procedure as well as build heap, I think the correctness is not given there by, I mean, as an induction, but the statement of invariant has been given there. Okay, so I request all of you to go through before the next lecture. That will be on Monday. We'll have tutorial, and hopefully, so now things kind of have settled from my family side. So hopefully by today evening, I should be able to give the recording of the solutions. Okay. Yeah. Okay, Girija, can you stop the recording?